presented by Caltech.
Before we start, I have a request. Please take a deep breath. It's going to be math intensive, okay? So just brace yourselves. There'll be stuff happening around, but follow along every step of the way. It won't be so hard, just a lot of things going on at the same time, okay? And the basic idea is very, very simple. It's what the name suggests. Separate them variables. That's all you got to do, okay? So let's talk about a setup in 2 dimensions. In Cartesian coordinates, so this is x and this is y, and say I'm looking at a certain region of this space. Okay? So for instance, I'm looking at the bounded box between y equals b and y equals a. Okay? I'm looking at what happens to oscillations inside this region per se. Okay? And you might ask, what is oscillating? This is not a membrane. This is not water surface. This is nothing. This is probability waves in quantum mechanics. Don't bother what it means today. Okay? I can go on forever about what the meaning might be of quantum mechanics, but for now we just shut up and compute. That's a German way of doing things. And this was a quote back in the day that you forget about what it means, you just solve it out. Okay? It was very successful, and it still is. So let's try and understand what happens in this region particularly. Okay? What is oscillating, the variable at least, is some psi. This trident symbol. People often get kind of worried about what that is. It just looks hard, it's hard to make. And if you're taking Quiz 2D next term, you'll be making that symbol all the time. So let's practice it. Okay? So what's oscillating is this capital psi function, which depends on where you are on that 2-dimensional plane, and also with time. So it's oscillating depending on where you are, and it changes with time. What equation does psi satisfy? The Schrödinger's equation, which you've already seen before in homework, so I hope it should look familiar now. So this is minus h bar squared over 2m. The Laplacian acting on psi x, y, t equals I h bar partial t capital psi x, y, t. Okay. And I'm restricting my attention only to this region bounded by this box. Okay? I'm not looking outside. So physically, it's the quantum mechanics of a particle which is bounded by these walls around here. Okay? So at these green walls and the axis walls, the potential energy goes to infinity. So it's like a hard wall. Okay? It's like a particle in a box. And you're going to hear this phrase a lot more in next term, so keep that in mind. The lonely particle is staying in a box. So that's the box. Okay? You want to solve for this equation in 2 dimensions. So the Laplacian operator in 2D, as you can guess by your homework problem, is the second x derivative and the second y derivative. In polar coordinates, it looks a little more complicated. It has 1 over r, 1 over r squared, sine thetas, a bunch of other stuff. But Cartesian stuff is nice and simple. Okay. Yes?
It's kind of a silly question, but why is it written with like an h bar squared on one side and h bar on one side rather than canceling?
Excellent. That's a very good question. The reason why we do that is this is not the full Schrödinger's equation. The full equation looks like as follows. H bar squared over 2m grad squared the Laplacian plus some potential depending on x, y, z, and t. This whole thing acts on psi, maybe z also if you're looking for the full thing, equals I h bar partial t psi x. So there is no obvious cancellation because you have the additional potential term. And to kind of like jump the gun and give you the crux of next term, this whole like thing with the Laplacian and the v is the energy of the particle. This is the momentum of the particle in quantum mechanics. So that's discussion one other time. So therefore you can't really cancel off generically, and hence to kind of keep intuition built up, we still put h bar squared and h bar there. If you want to be brave, like I am, what we do, we set h bar to 1. Then life becomes good. Then you don't have to worry about h bars whatsoever. Those are like God-given units. H bar is 1, C is 1, everything is 1. Yeah, it's a good life. Anyways, so that's my Schrödinger's equation. And I want to solve this. Notice first, this is a complex equation. It has i's floating in the equation itself. So in my setup today, don't be bothered by taking the real part in the end. Solutions can be complex. In your actual homework problem, the first two-way wave equation, that's a real wave equation, and therefore the oscillations are going to be real things in the end. Out here, no one's stopping you from complex stuff. And quantum mechanics, it's got to be complex, literally and figuratively. You know, this I really, the wave functions, these psi's have to be imaginary. They have to have an imaginary component. Okay? So we got to solve this. We will again look for very particular solutions as a warm-up to solve for this differential equation. Okay? We will separate the variables, which is a very generic trick in mathematical physics. What you do is you separate the variables. What variables do you have? X, Y, and t. 2 dimensions and time. Okay? So what we do is I take x, psi, x, y, t as a product function. I separate the variables into a space part with little psi. Okay? I hope you can make the difference out. Little psi x comma y and some function capital T of t. Just do it. Okay? We'll see why this is important. And if you have some foresight at this moment, you will realize that what we are doing today is what we did 1 week ago, exactly this last Wednesday, with 1 dimension. We had this chain of oscillators. We picked out the amplitude function and the normal mode e to the I omega t component, separated out the space and the time parts, doing the same thing here in a more formal way. Okay? So this is my ansatz. This is my guess. And if you're worried that this is not how like a solution would look like generally, you're right. This is a special solution. Don't be bothered, okay? Don't jump the gun completely and say, that's the final thing. No. Start here. Okay? You have a guess. You made an assumption about the variable dependence, plug it back. Okay? What do you get? On top, on the left-hand side, so minus h bar square over 2m. When you plug in the capital psi into the Laplacian is only space derivatives. Hence, it doesn't act on the time part. The time part for the Laplacian is like constant value. Okay? So it doesn't act on the t of t. It acts only on the little psi of x comma y. All okay with that? Just partial calculus. Equals I h bar partial t of capital psi. Now for the partial t, the spatial part acts as a constant, acts only on the capital T part. So you have little psi being pulled out like a constant, and then you have ddt of capital T as a function of t. I switched going from partial t to ddt because t is only a function of t. Okay? All okay with this? So this is generic how you would do it in 1D, 2D, 3D. It's the same thing, okay? You separate the variables out, space part, time part, and then you'll see what to do. Plug it back, separate the operations on the space, on the time, and then divide it by the solution again, by the ansatz, okay? So again, you divide it by capital psi x, y, t, which is the product little psi times capital T. Okay, divide it out. What do you get? The left-hand side, minus h bar square over 2m. You divide it out by capital psi. The capital T cancels off. You need to divide it out. So what you have is the Laplacian of little psi of x comma y divided by little psi x comma y. Psi. Do we all see that? I just divided this whole thing out by the product, and the capital T went away. On the right-hand side, I have I h bar. Divided out, this time the little psi cancels, and I have 1 over capital T of little t ddt of dt. Now this is where the magic will start happening. So far it was just algebra. Are we all okay with this reduction? I'm playing with a very special solution, the one which has a multiplicative dependence on the space part and the time part. Okay? I have not used the word normal mode so far. I have not used the word anything else. This is a math class. We're solving differential equations with partial stuff into it. Okay? And this is hard because it has second space derivatives, single time derivative. It's pretty high up there. Are we all okay with this? This is not easy stuff, so if you're bothered, please interrupt. All with me? Okay? Alright, sounds good. Now, look at this equation again. What does the left-hand side depend upon? X and Y. Is there any time on the left-hand side? No. Is there any spatial dependence on the right-hand side? No. So my separation of variables was literal. I could have my equation divided up into two parts. One part only on the spatial dependence, and the other only on the time dependence. And they're equal. Something moving in space, depending on where you are, you can choose X and Y where you want to be. This always equals some other function which is dependent on a whole other variable called time. And they are always equal. This is equal for all x, y, and t. And that's a lot to ask for. A function of space, its value, wherever you might be, is the same value that the time function obeys for all times. Question? Yes.
Would it be equal for all the x, y, and t, like inner A, B, like range, or is it like? Or does that
So right now I haven't imposed anything per se. So this is true for everywhere. I would eventually impose conditions, but this is more generic. So this is true everywhere. Do we all see that? Right? This is this should bother you. Does it bother you? Bothers me. Not anymore. I'm old now. I've seen this stuff like a million times. The only way a function of some variables is equal to another function of some other variables for all its arguments, it's only possible if the function is a constant. Otherwise, any little change in psi, little psi or capital T, would destroy that equality. The only way it's possible is that this thing equals to a constant. Now that's you can't derive that, you have to argue for that. Think about it, convince yourselves that the only way it's possible for these two to be the same is that they're both a constant. Yes, please.
Are we assuming beforehand that x and y and t are all independent?
Excellent, yes. So when you solve a differential equation, so x, y, and t are my independent variables. I'm looking for oscillations of psi depending on where I am and how it's changing in time. But I can independently choose where I am, x and y, and I can choose what time I'm looking at. So they're completely independent, yes. So x is not the label of a particle, neither is y. X and y are where you are on the 2D plane. Okay? Anything else? And I'm calling this constant E with some foresight. And we'll see why, but I'm going to call this E. And I'll also prove to you in a few minutes that this constant has to be real. So E must be a real number. It cannot be complex. The A functions, the size will be complex. The equation is complex, but the separation constant, as you want to call this, is not. Okay. Make sense? Okay. So I have some equation equals some other equation equals a constant. I can take the sum equation equals to the constant, the other one equals to a constant. I can break it up into two equations. Okay? So what do I get? The time part looks easier, so let's work with that first. So I have IH bar ddt capital T equals E. The time part of the equation. This seems easy. I can work with this pretty quickly. I have the capital T over capital T little t as a function equals minus I over h bar e dt. Just juggle stuff around. 1 over I is minus I. Okay? Just move the I down there. 1 over I is minus I, e over h bar. Okay. And I can integrate this out. It's a, yes.
Is there a t in the denominator in the first part? Yeah.
Yes, thank you. Yeah. Okay. So now I have an ordinary, not a partial, an ordinary differential equation in one variable. This we learned in high school, how to solve this. I hope. Yeah. We learned it in Caltech. Okay. Integrate this. What's the integration of dt over capital T? Natural log. This is ln t. I'm going to suppress the t index, the t argument is just cluttering things around. Equals, what about the integration here? I is a constant, minus is a constant, h bar is a number, e is a constant. Everything gets pulled out. I just have integral dt. What's that? T. Plus a constant of integration. So I'm indicating a first order differential equation. And this thing is just saying t of t is, let's call this, what you call it? Let's call this c as a constant, e to the minus I et over h bar. Now this c is from the integration constant. It's not something physical, it's just the integration constant of my differential equation integration. I exponentiate on both sides, e to the minus I et over h bar. I can absorb the constant in the amplitude. This is what I have. Are we all okay with that? Okay. I kind of want to go a little slow today with all this stuff because you're going to solve this again in the homework. Okay. And I want to see the outline of how this works because it's not the most trivial thing in the universe. All convinced with that? And now if you want to look for something else, the reason I chose the constant e, they called it e. Go back to your homework for a second. Remember how e we call this to be h bar omega in the homework? Now look at the t function under this identification. It's c. It's c e to the minus I, e over h bar is omega, e to the minus I omega. That should look nice. It's an oscillatory function in time. It just oscillates in time. Right? It's complex. Don't take the real part. It's a complex equation. In your homework, it will be the real one, but here is just the complex equation. Okay. So what do I have? What have I achieved so far? My solution, capital psi x, y, t, looks like the little psi x comma y, which I still haven't solved. I've solved the time dependence. It's some constant c, which I can absorb in psi, who cares, times e to the minus I et over h bar. Et, phone, home, that kind of stuff. People see et here? Okay, so it's carrying over generations. All okay with that? Just plug it back. And immediately what you realize, since e over h bar was omega, let's see what's happening. Every every location on that two-dimensional plane, for every xy, it's oscillating with the same frequency e over h bar, which is omega. And that should put a smile on your face. That's a normal mode. No? Gotta have some reaction. This is nice.
Can you say that again?
Yes. I separated things out. I solved for capital T. Okay. I got how t was changing in time. By my construction, the solution was separable. It's the space part times the time part. I absorb the constant c into the space part, I could, and I have the time oscillation, e to the minus I et over h bar. E over h bar is omega, that's e to the minus I omega t. So for every point on that 2D plane, x comma y, it has some amplitude depending on where you are, and it's oscillating with the same frequency omega. And normal modes were special configurations of all the particles for which each particle had the same frequency of oscillation. So separation of variables is the natural way to get a normal mode. Okay? So this thing is a normal mode of the Schrödinger's equation. I just had the time part so far. The space part is still to be solved. Yes.
Oh, so E here is energy, so you have, so each, in the separation of variables, each side is equal to some constant energy. What is the physical equation?
Don't ask me that. Don't ask me that. I can talk about it, but I think in the interest of time and for this course, I should not. We can talk about this after class if you want. But since you ask, and I'm a good person, the energy. So what happens is that in quantum mechanics, the energy is what, I mean in general in physics as well, energy is what drives time translations. If you have energy, that's why things move in time. So when you have energy, things are changing in time. And the way they are changing in time tells you how to move in real space. And that's what connects back to the spatial part of things. So that's all I'll say for now, but we can talk much more about this. And if you take physics 2B, and if I'm teaching, I can rank whatever about this.
Are you teaching?
I am hoping to. Yeah, I think I probably will. And quantum is like very close to my heart, so I think I'm all right. So we found a normal mode, but we still don't know what psi x comma y is, the spatial part. But I have an equation for psi from my separation of variables. What is that? The spatial part is minus h bar squared over 2m. The Laplacian, let's open this up again. Can we follow along a little more swiftly with this? So on the left-hand side, I have a 1 over psi. Let me pull that out. 1 over, actually, no, not right now. No, I changed my mind. Let's just do the way it is. Minus h bar squared over 2m Laplacian little psi x comma y equals to constant t. The second half of my separation. Okay. How do you solve for that? That looks hard by itself. Remember the wisdom. Whenever you have multiple variables, separate them. That's our border policy. Okay. Yeah.
Can you divide it again?
Yes, thank you. I don't like to divide things out. This is thank you. Okay. That's my second equation. So I have x comma y. I don't know what to do. I again separate stuff. So what I do is I make an ansatz, I make a guess. That little psi x comma y is some function which depends only on x times depends only on y. Again, very special solutions. Very, very special. But that's all I can do. I don't know what else to do. So that's my ansatz again. That the dependence is separated out. And you can see where this is going. Guess, plug it back. What do you have? So this is, I can move do I need to move that side? Maybe not. Let's just work with this. So I have minus h bar squared over 2m. The Laplacian on psi x comma y, where psi x comma y is x, x, y, y. When I do the Laplacian, it's the second x plus second y. The second x would only act on the capital X function. It would see y as a constant, just sees through it. Okay? So the first piece is the capital Y function divided by psi x comma y from the division that I had times d squared over dx squared capital X. Let me complete this and then we can have a look. Capital X, x over little psi x comma y d squared dy squared capital Y, y equals to We all see that. Plugged it, the y is a constant, gets pulled out, and had the division is there, x is a constant, second derivative of y. All with me? Excellent. Now, y over little psi. Y over little psi is 1 over x. Okay? So what do I have? Let's get this down, move the other board. Okay, so I have minus h bar squared over 2m. That gives me 1 over capital X, d squared x over d little x squared. I'm going to start suppressing arguments of function because it should be pretty evident what depends on what by the notation. Capital X depends on little x, capital Y on little y, capital D on t. You see the pattern going on there, right? Plus 1 over y, d squared y over dy squared equals to. Okay? If you want to make some sense, just also remove this x. So everything looks at the same footing now. Alright. Let's further massage this. H bar squared over 2m. 1 over capital X, d squared capital X over d x squared equals e minus h bar squared over 2m, 1 over y, d squared y over y. Plus. Thank you. All with me? Anyone lost in the algebra? Anyone? This is algebra thing, so anyone? Questions? Okay. All right. So the same thing. The left-hand side, what does it depend upon? X. Right-hand side, y. A function of x equals a function of y for all x and y. What must happen? Must be a constant. Let's call this constant e sub x. Let's call it. Okay? Once you call it, I can again have two equations. My first equation, the x equation, is minus h bar squared over 2m, 1 over capital X, d squared capital X over d x squared equals ex. Hence, d squared capital X over d x squared equals minus 2m ex over h bar squared times x squared. Let me complete things and then we talk more about this. And similarly, here you have, I have minus h bar squared over 2m 1 over y d squared y over dy squared equals e minus ex. Just move stuff around. I'm going to call this ey for compact notation. And then what I have d squared y over dy squared equals minus 2m ey over h bar squared times ey. Alright. Now that should look really nice to everyone. If you have one thing to take away from this whole 10 weeks, take away the fact that you can solve for this differential equation in a jiffy. What equation is that? The simple harmonic oscillator. I boiled down my Schrödinger's equation into two simple harmonic motions in x and y and some oscillation in time. Pretty sweet. Let's call this bracketed, again, I'm defining stuff as so should you in your life. When you see hard algebra, be it the midterm or be it a research problem or be it just for fun, stop writing things over and over again. Call them something else. It'll ease your life. Okay? So let's call this thing as kx squared. So this orange thing without the minus is kx squared, and the purple, I don't know what color this is, this stuff is ky squared. Okay? Alright, can someone tell me solutions for this? What's capital X of X and what's capital Y of Y? Simple harmonic motion. A sine, and then maybe with the cos first. A cos kx x plus b sine kx x, and the y function is some other constant c. Yeah, I don't want to use the same c. D. D cos ky y plus e sine ky y. Do we all see that?
Is it this? It's a different year.
It's a, oh yeah, oh, this is a mess. 26 is not enough.
Call it alpha and beta.
Or give it like stars and smiley face on
Okay.
No, don't do that.
I'm putting a turban on all the F's. G? Okay, G. You all okay with that? What's my final solution then? Capital psi x, y, t is a cos kx x plus b sine kx x acting on d cos ky y plus g sine ky y times e to the minus I e t over h bar. Ta-da! It's solid. You plug this back, it is a solution to my Schrödinger's equation. Okay? Now, let's get back to what that bounded box looks like. Now this is the analog of a generic normal mode in one dimension, now in 2 dimensions. Now we try and find standing waves. Standing waves are normal mode plus boundary conditions. I had no boundary conditions yet. Now I'm going to impose them. Okay? So for example, I'm going to make this quick, and because the homework will make you do this in more detail, and I want you to suffer on your own. I won't do much. So boundary conditions. Again, example. This is one kind of boundary condition, it's not always true. But say that psi, capital psi, along the axis, the x-axis between 0 and a, I'm only focusing on the box now. Now I'm focusing on the box, okay? Everywhere outside, I don't care. It's happening in the box. That's where the party is at, okay? Psi, for all x, for 0y, for all t, is 0. And I'm looking for x between 0 and a, and y between 0 and b for all time. That's my bound on my variables. And I'm demanding that along this axis, from 0 to a on the x-axis, the function always vanishes. Like a closed condition when you had the fixed, one of the ends was fixed. This is one of the ends on the 2 dimension being fixed. The wave function is going to 0 at that point. When you have that, what happens? When you plug in y to 0 in my normal mode solution, when y is 0, so the x part is 0, when I put y to 0, the sine kyy is automatically 0. All I have left is d cos kyy. Cos kyy for y0 is 1. So it's d times some x part times some t part. And it always vanishes. What does that imply? Just like in the one dimension case, the standing wave was a cos kx plus b sine kx. The left end was fixed, hence the cos term went away, the A with the cos went away. Similarly, the cosine term went away. Let's do that again. What about this edge? Say this is also 0. Example, alright? So psi for 0x, for all y, being the bound for all t is 0. What does this imply? What vanishes now? A. Do we all see it? If anyone doesn't see it, please just give me a sign. I can walk through this again.
Does the cosine term also disappear or
No, the cosine is there, but the coefficient went away, so even the cosine goes away, right? But we argue the fact that, let's look at the other one. So when x is 0, so the sine kx, the sine goes away. The cos kx 0 is 1. So you have just a times 1 acting on some function of y, some function of time. That's true for all y and t. And this is 0 for all y and t. It's only possible when that number vanishes itself. This implies. Okay, I'm going to stop here with this stuff because otherwise I'll be giving away too much for the homework, I think. What about conditions on these pieces, on the green ones? What happens because of those? Just physically, what would happen to other stuff? If I specify what is happening on the x equals a or the y equals b line, what would that do? It was quantize the case. So for example, if I'm specifying that they both are fixed as well, there's 0, the kx and the ky would become quantized. Okay? And I don't think I want to do that today. Okay. But the idea being that you could work out other conditions, like what psi is at x equals a, y, t. It will be something known. Solve for it. Psi x, y equals b, comma t. Solve for it. Get the conditions on kx. You'll only have two unknown constants which get fixed by the initial shape of the wave function. Say someone then specifies to you what psi x, y, and t is. At t equals to 0, just like the guitar string that we had before. You pluck it at the start, its initial shape. Now this shape, you can write it down, and the big takeaway, maybe I should just do this right now. I think I want to do this. I changed my mind again. I want you to see this. Now say I demand the fact that even on these other edges, the green ones, the function vanishes. So 0 here as well. What do I get because of this? Let's be quick about this. If it's vanishing at the x equals a boundary, the a already went away because of this condition. B sine kx a equals 0. B can't be 0, hence sine kx a equals 0. Therefore kx a is quantized, and this will give me kx is n pi over a. And this will give me ky equals some n prime pi over a, n equals 1, 2, so on and so forth, n prime equals 1, 2, so on and so forth. So we all see that?
Over B.
Over B, thank you. Do we all see that? Just that other boundary condition, now in 2 dimensions, it's at a line or not a point. And what is the general solution now? We found the normal modes. We found the Fourier terms. A general solution is just sum over all these Fourier transform terms, right? So psi x comma y comma t, general solution is sum over n and n prime. I have bn sine n pi x over a times c, or what was I calling it? G n prime sine n prime pi x over b e to the minus I omega t. But omega also now depends on n and n prime. How? What was omega? Omega was e over h bar, and e was ex plus ey. which you can see from up there. E minus Ex is Ey. Okay. And remember how I defined the k's. The k's were defined as, so k squared, kx squared was 2m Ex over h bar squared, and ky squared was 2m Ey over h bar squared. Yes?
Sorry, no y instead of where the x is in the second.
Y, thank you. Yeah. Too many variables floating around. Okay? Yeah. So that's kx, that's ky. I can plug it back, solve for the e's from here, and you have omega equals h bar over 2m kx squared plus ky squared. And that, friends, h bar k vector mod squared. The same dispersion relation that you found on your homework. By plugging in that silly ansatz of an exponential into the Schrödinger's equation. So this time we solve for omega. Now omega, of course, depends on kx and ky. And kx and ky are both quantized with m and n prime. Hence even omega depends on n and n prime. Okay? That's the general solution. How do you fix these constants? You can always club them into one if you like, but it's better to keep it separate for now. You match it as the Fourier transform, do the Fourier inversion trick to find what the constants are by mapping it to the initial shape psi xy at 0 time. This is that equals to 0. You map it, do the Fourier inversion, get the constants as the generic solution. This is the analog of that guitar string thing that we did on Friday in 2 dimensions now. You have, let's recap. Wave equation, we solved it by separation of variables. Separated solutions were normal modes. By the boundary conditions, they became standing waves. By one thing being fixed, some coefficients went away. The other end being fixed, the case became quantized. The general solution is a sum over all the normal modes, and you fix these constants by mapping it to the initial shape at t equals to 0. I went a little fast here because part of this are going to be the homework. You're going to see it again. Okay?
Could you go over again with mapping?
Yeah, so what I mean by this is someone tells you what the shape is at t equals to 0. Okay? So psi x comma y comma 0. So it's some function px comma y, which is a known function. Someone tells you how the thing starts at t equals to 0. Now this is some n prime, that same thing. The exponential at t equals 0 becomes 1. So you only have bn, the sine first term, d, or what was it, g n prime sine of the second term with a y. To find the b and the g's, you do the Fourier inversion trick. Multiply both sides by one of the signs, integrate, orthonormality, delta functions. It's a whole bunch of stuff to be done. But the idea is that known function, you're Fourier decomposing it into a bunch of other Fourier terms. How do you find the coefficients? You invert. Okay. And you probably, we're not going to ask you to invert the 2-dimensional one in this class. That's a lot of work. Okay. The homework is only going to ask you to solve till here. The same thing. It's a different shape in the sense of the shape in the homework is between minus a to a. So it's shifted. That's something different about the thing. But this was not trivial. Like, lot just happened, right? So for the homework, don't be scared to how do I approach it? What's the final answer? Do this thing again. It's going to take like 20 minutes, 30 minutes, but do it. Please. It'll like,
When you change the boundaries condition, that only changes like all the values you get on that side, but all the like derivations to get the equation for the.
Everything stays the same. Up till here, up till the generic normal mode, there was no reference to boundary conditions. Only after this, I combined the normal mode with boundary conditions, and then that became standing waves. And standing waves are these Fourier decomposition stuff, which make up any general solution. All right, any other questions? How are we on time? We have about 7 to 10 minutes.
When we solved for the time function, we separated little phi and time. We said that we could feel like that's normal, that's still the normal mode because for any x and y, they oscillate with time function. But then when we solved for little phi, it would also oscillate like the simple harmonic stuff. So how are those still normal modes if the oscillations depend on x and y in addition to time?
So just let's go back to the basic situation where you had these two pendulums, right? So one of the normal modes was this in sync oscillation, other was the out of sync oscillation. Okay. So the normal mode what this is saying is that the position could depend on which particle you are. But the frequency of oscillation, the time it takes to complete one cycle, doesn't depend on the position. So even on this, let's say on this two-dimensional plane, if I take this point and this point, they might have different values at a given moment of time, but the time they take to complete one cycle to get back to the same value is the same because the frequency is the same. One might start here, let's say simple one-dimensional oscillator. One might start here, one might start there, and they might oscillate in different ways, in different they're not overlapped. The point being that they just have the same frequency. You see what I'm saying? Right? Okay. Any other questions? Because once you're okay with this, we shut this topic down and we go to interference, like electromagnetic waves, the Young's double slit experiment, and a whole bunch of different ideas. But this is done, if you're okay with this. What I'm going to do is, have you all seen the Young's double slit experiment before? At least solved for it in class sometime? It was physics 1C, 1B? 1C. And what disappoints me a lot is that if you're not a physics major, you would always show you the same thing over and over again. You would talk about the two slits, there's light coming in, look at the path difference, we say if it's a integer multiple of 2 pi, there's constructive interval, it's a maxima, it's a minima. I want to show you a little bit more because I think it's exciting to see what the real pattern looks like. And have you heard things like the pattern is only important when the two slits, their distance is order the wavelength? Have you heard this line? And no one ever justifies this, I have seen. Like when I was younger like you and I was being taught this, I was always worried. Why is it only true that when the slit distance is order wavelength or more or whatever, is then you see the actual pattern on the screen, otherwise not. When you see it in the math, someone already showed you in the math, but I think kind of short on time today, we're going to start a new topic. And I do want to mention that the quantum Young's double slit experiment is a whole monster by itself. We won't talk about that this time. But the cool part is that you have this, you shine light across the slits, you see a pattern. Quantum mechanically, if you go and observe one of those slits, if you go and look at it, look has a particular meaning in quantum mechanics, but if you go and observe one of the slits, the pattern vanishes. And if you're not looking at the slits, but you're looking at the screen, the pattern is back. This has been observed experimentally. This is how the real world works. And quantum mechanics is really, really bizarre at its heart. Ideas like entanglement and a whole bunch of other things. I could ramble on about this forever, but I don't know physics to be part of it. So, I noticed something. It's weird. Whenever I drive into campus every morning from home, I like stay right by the edge of campus, but I drive still because I'm late every morning for class. So I drive. The FM just plays Ramble On pretty often by Led Zeppelin for some reason. I don't know why. It's always happens every morning, almost every morning. It's weird. It's kind of weird. Yeah. Anyway, so we'll talk about the double slit experiment next time in detail, and hopefully this stuff made sense. If you have questions, I'm around for the next few minutes. Ask me otherwise.